Let us sum up the domain and range of all the trigonometric functions that you studied in class 11th. The sine function has the set of real numbers as its domain and the closed interval -1, 1 as the range. The cosine function has the set of real numbers as its domain and the closed interval -1, 1 as the range. Similarly, the domains and ranges of other trigonometric functions, namely tangent, cotangent, secant, and cosecant, are shown here. Let us also recall the concept of the inverse of a function. If a function f from set x to set y, defined by f of x is equal to y, is 1 to 1 and onto, then there exists a unique function g from set y to x such that g of y is equal to x. Such a function g is called the inverse of function f and is denoted by f with superscript -1. Now, using the concepts of the inverse of a function and the domain and range of trigonometric functions, let us find the inverse trigonometric functions. Let us begin with the sine function. As the values of sine 0 and sine pi are equal to 0, it is not a 1, function. On restricting the domain to -pi upon 2 to pi upon 2, the sine function becomes 1, and onto with its range as closed interval -1, 1. In such a situation, the sine function is a bijection, and therefore its inverse exists. Sine inverse of sine of x is equal to sine of sine inverse of x, which is equal to x. Further, even if the domain of the sine function is restricted to the intervals shown here, its range will still remain the same. Now, let us define the inverse of the sine function in the given intervals. The domain of the sine inverse is closed interval -1, 1, and its range is closed interval -pi upon 2 to pi upon 2. The branch with the range -pi upon 2 to pi upon 2 is known as the principal value branch of the sine inverse function. Remember that if y is equal to sine inverse x, then sine y is equal to x. The graph of the sine inverse can be obtained by interchanging the x and y axes in the graph of the sine function. Let's now proceed to the cosine function. As the values of cos 0 and cos 2 pi are equal to 1, it is not a 1, function. On restricting the domain to 0, pi, it becomes 1, and onto with the same range. In such a situation, the cosine function is a bijection and its inverse exists. Further, if the domain of the cosine function is restricted to the intervals shown here, then also the range is closed interval -1, 1. Now we can define the inverse of the cosine function in the given intervals. The domain and the range of the cosine inverse function are closed interval -1, 1 and closed interval 0, pi, respectively. The branch with the range 0 to pi is known as the principal value branch of the cosine inverse function. The graph of the cosine inverse function can be obtained by interchanging the x and y axes in the graph of the cosine function. Similarly, working on the same lines, the other four inverse trigonometric functions can be defined. The domain and range of the inverse cosecant function is shown here. The principal value branch of cosecant inverse is closed interval -pi upon 2, pi upon 2, excluding 0. Here are the graphs of the functions cosecant, and its inverse. The domain and range of the inverse secant function are shown here. The principal value branch of secant inverse is closed interval 0, pi, excluding pi upon 2. Here are the graphs of the functions secant and its inverse. The domain and range of the inverse tangent function are the set of real numbers to open interval minus pi upon 2 to pi upon 2. The principal value branch of tan inverse is an open interval minus pi upon 2, pi upon 2. The graphs of the functions tangent and its inverse are given here. The domain and range of the inverse cotangent function are the set of real numbers and open interval 0, pi, respectively. The principal value branch of the cotangent inverse is an open interval 0, pi. The graph of the functions cotangent and its inverse are given here. The value of an inverse trigonometric function which lies in the range of the principal branch is called its principal value. This table summarizes the principal value branches of all inverse trigonometric functions. Before we begin a discussion on the properties of inverse trigonometric functions, let's quickly revise what you have learned so far. If sine inverse x is equal to y, then sine y is equal to x. Also, sine of sine inverse of x is equal to x, where x belongs to a closed interval minus 1, 1. Similarly, sine inverse of sine x is also equal to x when x belongs to a closed interval minus pi upon 2, pi upon 2. You also learned about inverse trigonometric functions and their principal value branches. Let us now prove some properties of inverse trigonometric functions. The first property states that sine inverse of 1 upon x is equal to cosecant inverse x. Also, cos inverse of 1 upon x is equal to secant inverse x. Similarly, tan inverse of 1 upon x is equal to cot inverse x. Now, let us prove that tan inverse of 1 upon x is equal to cot inverse of x. Denote cot inverse x by y, which implies that x is equal to cot y, or 1 upon x is equal to tan y. This further implies that y is equal to tan inverse of 1 upon x. Finally, substituting the value of y proves the result. Similarly, the remaining two properties can also be proved. The second property states that sine inverse of minus x is equal to minus sine inverse x. Similarly, tan inverse of minus x is equal to minus tan inverse x, and cosecant inverse of minus x is equal to minus cosecant inverse x. Consider the second part. Let us denote tan inverse of minus x by y. This implies tan y is equal to minus x. It can also be written as x is equal to minus tan y or x is equal to tan of minus y. Now, tan inverse of x is equal to tan inverse of tan of minus y. This implies tan inverse of x is equal to minus y, since tan inverse of tan theta is equal to theta. Substituting the value of y gives tan inverse x is equal to minus tan inverse of minus x. On multiplying both the sides by minus 1 gives the result, that is, tan inverse of minus x is equal to minus of tan inverse x. The other two properties can be proved in a similar way. The third property states that cos inverse of minus x is equal to pi minus cos inverse x. Similarly, secant inverse of minus x is equal to pi minus secant inverse x. Also, cot inverse of minus x is equal to pi minus cot inverse x. Let us prove the first part. Cos inverse of minus x is equal to pi minus cos inverse x. Let us assume cos inverse of minus x is equal to y. This implies cos y is equal to minus x, or x is equal to minus cos y. Further, minus cos y can be written as cos of pi minus y, since cos pi minus theta is equal to minus cos theta. This can be written as cos inverse x is equal to pi minus y. Substituting the value of y, we get cos inverse x is equal to pi minus cos inverse of minus x, or cos inverse of minus x is equal to pi minus cos inverse of x. In a similar manner, the remaining two properties can also be proved. The fourth property states that sin inverse x plus cos inverse x is equal to pi upon 2. Also, tan inverse x plus cot inverse x is equal to pi upon 2. Similarly, cosecant inverse x plus secant inverse x is equal to pi upon 2. Let us prove tan inverse x plus cot inverse x is equal to pi upon 2. Denote tan inverse x by y. This implies x is equal to tan y. Now, tan y is cot of pi upon 2 minus y. This implies x is equal to cot of pi by 2 minus y. Taking cot inverse on both the sides, we get cot inverse x is equal to pi upon 2 minus y, which can be written as cot inverse x plus y is equal to pi upon 2. Substituting the value of y, we get cot inverse x plus tan inverse x is equal to pi upon 2. The other two properties can be proved in a similar way. The fifth property states that tan inverse x plus tan inverse y is equal to tan inverse of x plus y upon 1 minus xy, and tan inverse x minus tan inverse y is equal to tan inverse of x minus y upon 1 plus xy. Let's prove the first property. Denote tan inverse x by a and tan inverse y by b. This implies tan a is equal to x and tan b is equal to y. Now, tan of a plus b is equal to tan a plus tan b upon 1 minus tan a into tan b. Substituting the values of tan a equal to x and tan b equal to y in the equation, we get tan of a plus b is equal to x plus y upon 1 minus xy. This implies tan inverse of x plus y upon 1 minus xy is equal to a plus b. Substituting the values of a and b, we get tan inverse of x plus y upon 1 minus xy is equal to tan inverse x plus tan inverse y. The other property can be proved by following the same method. The sixth property states that 2 tan inverse x is equal to sine inverse of 2x upon 1 plus x square. Also, 2 tan inverse x is equal to cos inverse of 1 minus x square upon 1 plus x square, and 2 tan inverse x is equal to tan inverse of 2x upon 1 minus x square. Let's prove the first one. Let us assume that tan inverse x is equal to y. This implies x is equal to tan y. Consider the right-hand side. Sine inverse of 2x upon 1 plus x square. Substituting tan y in place of x, we get the right-hand side as sine inverse of sine 2y. This is because 2 tan theta upon 1 plus tan square theta is equal to sine 2 theta. This is further equal to 2y or 2 tan inverse x, which is the left-hand side. Hence the result. In the same way, the other two properties can be proved.